Welcome to this AS Physics tutorial. In this tutorial, we want to look at error and uncertainty. More specifically, we want to look at all the theory that you need to know for this topic, as well as all the computations or basic methods for calculations. This tutorial is based on an analysis of 20 past exams. Question 1 here deals with the definitions of precision and accuracy. It says complete the following, and in 1.1, the precision of a measurement refers to, now the precision of a measurement refers to how close measured values, so measured values are to each other. So in physics, when we want to measure something, we won't just make or take one measurement. We'll repeat the measurement a few times, like 3 to 5 times, and then take an average. If the repeated measurements are close to each other, then we'll say that the measurement is precise. Then in 1.2, it says the accuracy of a measurement refers to. Now, the accuracy of a measurement is not the same as the precision of a measurement. The accuracy refers to how close a measurement, so how close a measurement is to the true value. So, for example, if you're measuring someone's height, we mentioned that you won't just do one measurement. You'll do a few measurements. In other words, you'll repeat the measurement a few times and then take the average. If that average is close to the true height of the person, in other words, the true value of the measurement, then we'll say that the measurement is accurate. Then in number 2, it says, explain how the accuracy of a measurement can be increased. In other words, how can we get a measurement to be closer to the true value? We can do this by making repeated measurements. So making repeated measurements and then finding an average or taking an average. So an average or a mean value. In question 3 it says, consider the dartboards shown below. Match each statement, so each of these statements, with the correct diagram by writing the letter next to it. What's important to note here is that the bullseye or the center of the dartboard is analogous or refers to the true value of a measurement. So the closer the darts are to the center or bullseye, the more accurate a measurement will be. Then the distance between the darts is analogous to the precision of the measurement. If the darts are close together, then we know the measurement will be precise. If they're far apart, we know it will not be precise. So let's consider A. In A, all the darts are close to the bullseye or the center. So we know this is accurate. It represents an accurate measurement. The darts are also close together, close to each other. So that means the measurement is also precise. So it's both accurate and precise in A. So 3.3 will be A. In B, the darts are all far from the bullseye, so we know the measurement is not accurate. However, they're close together, close to each other, so we know it's precise. So it's not accurate, but precise. So precise but not accurate will be B. In C, the dots are all fairly close to the bull's eye, so it's accurate, but they are fairly spaced out or far from each other. So this will be accurate but not precise. So it will be 3.1, or 3.1 will be C. Then in D, the dots are all far from the bull's eye, so we know this measurement is not accurate. They are also spaced out. They are not close to each other, so it's not precise. So it's neither accurate nor precise. So 3.4 will be D. In question 4.1, we have to explain what is meant by a random error. Now, a random error is an error that causes unpredictable, fluctuations in an instrument's reading. So it's an error that causes unpredictable fluctuations in an instrument's reading as a result of uncontrollable factors. An example of uncontrollable factors are environmental factors, such as temperature. So when you do a reading, or a measurement rather, in a room, you may find that the temperature fluctuates in the room. And as a result, it causes fluctuations in an instrument's reading. So in question 4.2, we have to say what a systematic error is. A systematic error is an error that is due to faulty instruments. So due to faulty instruments or flaws in the experimental method. So it's important to note that a systematic error will occur every time the instrument is used or the experimental method is applied. Then in 4.3, we have to give an example of a systematic error. Now, an important example of a systematic error is the zero error. Now, what is the zero error? The zero error is when an instrument shows a reading when the reading should be zero. So when an instrument shows a reading when it's not being used. So every time you use the instrument, it will show a reading greater than what it actually should be. This is an important example of a systematic error. And remember that a systematic error occurs every time you use the instrument. In question 5 here, we have to complete the statement by filling in the missing part. A random error affects the precision of a measurement. So a random error will cause the measured values to be far from each other or far apart. Then in 5.2, a systematic error affects the accuracy of a measurement. So a systematic error will cause the measurement to be far from the true value. In question 6, it says, suggest a way in which each of the following can be reduced. And in 6.1, a random error. We can reduce a random error by taking several measurements. So take several measurements. and then calculating an average or the average. So take several measurements and calculate the average. Then how can we reduce a systematic error? A systematic error can be reduced or minimized in two ways. Firstly, we can recalibrate instruments or an instrument. So recalibrate the instrument. Or adjust or correct the experimental method. Remember that a systematic error arises either from faulty instruments, in which case we can recalibrate the instrument. It could also result from an incorrect experimental method, in which case we can adjust or correct the method. It says complete the following. Uncertainty is an estimate of the difference between a measurement or actual reading. So we can write measurement or actual reading and the true value. So the true value of the quantity which we want to measure. Then in question 8.1 it says, write down the reading on the ammeter below. This is an analog ammeter, together with its absolute uncertainty. So let's first find the reading. Now on this ammeter we have large divisions. So for example 1, 2, 3, 4, 5. So each of these large divisions represents 1 milliamp. Then within a large division we also have 1, 2, 3, 4, 5 small divisions. So we want to get the value of a small division. So we first want to get the value of a small division. And this will be the smallest division on this ammeter. So we know that there's one large division here with 1, 2, 3, 4, 5 small divisions. So one small division will represent 1 divided by 5, which is 0.2 milliamps. So then to do the reading, we'll have 1, so 1 milliamp up to this point, then 1, 2, 3 small divisions, so 3 times 0.6. So basically the reading then will equal 1, so 1 large division, so 1 milliamp, plus, and we said there are 1, 2, 3 small divisions, so 3 times 0.2 milliamps. One small division is 0.2 milliamps, and this gives us 1.6 milliamps. So then the reading itself will be 1.6. Now we have to find the absolute uncertainty. So let's do that. Now the question is, how do we get the absolute uncertainty? The absolute uncertainty on an analog instrument will always be half the smallest division. And we know that the smallest division is 0.2 milliamps. So we also use the symbol delta for absolute uncertainty. In this case, we're working with current, so the absolute uncertainty will be delta I. And we said it's 1/2 times the smallest division. So 1/2 times 0.2. And of course, this is 0.1 milliamps. Then in 8.2 it says, write down the range of values in which the true value of the current is believed to lie. So we need the range of values, and we can use a calculator here. To get a lower boundary of this range of values, we're going to take the measurement and we're going to subtract 0.1. So we subtract the absolute uncertainty, and this of course is 1.5. Then we're going to take the measurement 1.6 in order to get the upper boundary of this range, and we're going to add the absolute uncertainty, and this is 1.7. So we are confident that the true value, the true measurement of the current lies between 1.5 and 1.7, between 1.5 and 1.7. Then in question 8.3, it says write down the formula for percentage uncertainty. So the percentage uncertainty is the absolute uncertainty divided by the measured value, and we can just write value for measured value, and this is multiplied by 100 in order to get a percentage. Then in question 8.4 it says calculate the percentage uncertainty for the ammeter reading in question 8.1. Now recall that in question 8.1 the ammeter reading was given as 1.6 plus minus 0.1 milliamps. So the measured value together with the absolute uncertainty. We can use this equation. So percentage uncertainty will be the absolute uncertainty, which we can write as delta I for current, over the value or measured value, which is I, and we multiply this by 100. So it's going to be 0.1 for delta I over 1.6 multiplied by 100. And we can do this on a calculator. And it comes to 6.25%. Now, what's important to note here is that the absolute uncertainty that we used in this calculation is given with one significant figure. And that means that we must also give the percentage uncertainty to or with one significant figure. So we're going to write it as 6%. In question 9 it says a measured value for power is 50 watts with a percentage uncertainty of 5%. Calculate the absolute uncertainty of the measurement. We know that the symbol for power is capital P, and we are given its percentage uncertainty. So the percentage uncertainty, of course, is delta P over P times 100. And we know that this must come to 5. We want the absolute uncertainty delta P. So we need to make it the subject of the formula. So we can divide the 100 into the right-hand side and then multiply by P. On a calculator, this comes to 2.5 watts. Now we need to give it to the correct, or with the correct number of significant figures. The percentage uncertainty that we were given has one significant figure. So our answer here for the absolute uncertainty must also be with one significant figure. Here we have two significant figures. And since the first digit after the decimal point, or the digit after the decimal point, is 5, we can round it up to 3. So then the absolute uncertainty with one significant figure is 3 watts. In question 10, we have to write down the absolute uncertainty of the reading on the digital ammeter here. So how do we find the absolute uncertainty on a digital instrument? It's quite simple. We look at the least significant figure, which is a 7 here. We replace it with a 1, and then we have leading zeros. So it's going to be 0.01. In question 11, it says, find the absolute uncertainty of the following data set of the diameter of wires. And we are given these values. So these are repeated measurements for the diameter of a wire. We need to find the absolute uncertainty. Now, the rule for the absolute uncertainty, we can call it delta D for diameter. So the absolute uncertainty of the diameter. The rule is that for repeated values, the absolute uncertainty will be a half times the range. And the range is the maximum value minus the minimum value. So a half times the range. So what is the maximum value? It's 0.42 less the minimum value, which is 0.39. And this is a half into 0.03. We can do this on a calculator, and it comes to 0.015. So that's the answer that we would write in here. Note that these values are all given with two significant figures, and hence our answer must also be with two significant figures. Then in question 12.1, it says 2 voltages are measured, 5.0 plus minus 0.1 volts with a digital voltmeter, and 4.0 plus minus 0.2 volts with an analog voltmeter. Find the total voltage together with its absolute uncertainty. So this question has to do with combining uncertainties. Let's first find the total voltage, and we can call it VT. To get the total voltage, we simply add the measured values, these two voltages. So 5.0 plus 4.0. And this is 9.0 volts. The question now is, how do we combine the uncertainties? Note that we're adding here. We're adding two quantities. Now, the rule says when we add quantities, we simply add the uncertainties. So then the uncertainty, delta Vt, or V sub t, so the uncertainty of the total voltage, will simply be the sum of these uncertainties. So 0.1 plus 0.2, and that's 0.3. In question 12.2, it says the diameters D1 and D2 of two spheres are measured. So we're given the measurements here together with their absolute uncertainties. Find the difference D1 minus D2 between the diameters together with its absolute uncertainty. So let's first find the difference D1 minus D2. So that's simply going to be 45.0 minus 22.0. And this, of course, is 23.0 centimeters. The question now is, how do we find the absolute uncertainty of a difference of two quantities. And the rule says that when we find the difference between two quantities, we add their absolute uncertainties. So we don't subtract them, we add them. So the absolute uncertainty then in a difference, D1 minus D2, will be the absolute uncertainty of D1. So the absolute uncertainty of D1 plus the absolute uncertainty of D2. So important to write out this equation because you get a mark for this in the exam. So then it's 0.5 plus 0.4. Which is 0.9. And we saw that the difference D1 minus D2 came to 23.0. Let's look at 12.3. It says a moving object covers a distance x in a time period t. And we are given these values for x and t together with their absolute uncertainties. Calculate the average speed, v bar, of the object together with its absolute uncertainty. So let's just find the average speed. We know that it's distance over time. So x over t, the distance x is 20.0 and the time t is 2.00. And this comes to 10. Important to note that the values that we used in our calculation both have 3 significant figures. So our answer must also be be with 3 significant figures. So we can write it in here. Now we need to find the absolute uncertainty of V bar. Now we get V bar by dividing two quantities, namely distance and time. The rule says that when we divide quantities, the way in which we combine their uncertainties is by adding the percentage uncertainties. So we don't add the absolute uncertainties, we add the percentage uncertainties. And that will give us the percentage uncertainty of V bar. So before we can find the absolute uncertainty of V bar, we first find the percentage uncertainty. So the percentage uncertainty in V bar will be the percentage uncertainty in X plus the percentage uncertainty in T. It's very important to write down this equation in the exam in order to get a mark for it. So we can plug in the values. Delta X is the absolute uncertainty in X. X is the measured value or value. Delta T is the absolute uncertainty in T divided by the measurement. We can do this on a calculator and it comes to 1%. Now that we have the percentage uncertainty in V bar, we can find the absolute uncertainty. So the absolute uncertainty in V bar will be the percentage uncertainty, 1%, so 1 divided by 100 times the measurement, or times the value we got for V bar, which is 10.0. And this is 0.1. Once again, the absolute uncertainties given in the question had one significant figure. So our answer must also have one significant figure. And this, of course, should be V bar. Let's go on to 12.4. It says the radius of a sphere is measured as 2.40 plus minus 0.02 centimeters. Find the volume of the sphere together with its absolute uncertainty. And we are also given the equation for the volume of a sphere. So then the volume will be 4 over 3 pi times r cubed, so times 2.40 cubed. And on a calculator, this comes to 57.9 centimeters cubed. Once again, we must give our answer with 3 significant figures, because the value that we used here for the radius has 3 significant figures. So 57.9. We must find the absolute uncertainty for the volume. Now, note that we get the volume by raising the radius to the power of 3. The question is, how do we combine uncertainties when we raise quantities to a power? And the answer to that question is that the way we combine uncertainties when we're raising to a power is to multiply the percentage uncertainty by the power. So before we can find the absolute uncertainty in V, we'll first find the percentage uncertainty. And that's the percentage uncertainty in R multiplied by the power of 3. And of course, we can do this on the calculator. Delta R over R and we get 2.5%. Now we can find the absolute uncertainty in V. So we can find delta V is just going to be the percentage uncertainty multiplied by the measurement. And we get an answer of 1.4475. Now, we need to look at the number of significant figures given in the data that we used. Here we only have one significant figure for the absolute uncertainty in R. So our answer here must also be with one significant figure. So it's simply going to be 1 then. In question 13 it says, the period T of the oscillations of a mass M suspended from a spring is given by this equation, where K is the spring constant of the spring. Then it says the manufacturer of a spring states that it has a spring constant of this amount and a mass of this amount. And it's suspended from the end of the spring and then made to oscillate. So we're given the spring constant with its percentage uncertainty here and the mass with its absolute uncertainty. In the first question, we have to calculate the period T of the oscillations. So that we can do quite easily. We just plug into our equation. The mass M is 200 times 10 to the negative 3. And over K, which is 25 newtons per meter. So let's work that out. And we get this answer, so 0.56. Now, just note that we give the answer with two significant figures because the maximum number of significant figures in this calculation was 2. It's a 25 here, which is two significant figures. Then in question 13.2 it says, determine the value of t with its absolute uncertainty to an appropriate number of significant figures. Now, let's go back to how we got t. It's by using this equation. And you can see that we're taking the square root of m divided by k. Now, recall that the rule says when we divide quantities, then the way in which we combine the uncertainties is by adding the percentage uncertainties. So we need to add the percentage uncertainties of m and k. We already have the percentage uncertainty of k. We just need to find the percentage uncertainty of m. So let's do that. It's going to be delta m over m. In other words, the absolute uncertainty divided by the measured value. And then, of course, multiplied by 100. And we get 2%. So now we can find the percentage uncertainty of t. So we said because we are dividing two quantities, we must add their percentage uncertainties. So it's going to be the 2% plus the 8% for k. So 8% for k. Now, the question is, what do we do with the square root? Important to note that the square root is the same as to the power of a half. So this formula could be rewritten as 2 pi into m over k to the power of a half. And the rule says that when we raise something to a power, we multiply the percentage uncertainty by the power. In other words, we need to add the percentage uncertainties of m and k, and then we need to multiply it by a half. So that's 10% times a half, which is 5%. Remember, we want the absolute uncertainty of the period t. We've got the percentage uncertainty here. So then the absolute uncertainty of t, delta t, will be this percentage times the value we got for t. And we get an answer of 0.028. This is to two significant figures. Now, we need to be careful here because the uncertainty, the percentage uncertainty given here, which we used in our calculation, has one significant figure. And the same here, one significant figure. So we need to give our answer then with one significant figure. So it's going to be 0.03. Then, of course, the period that we calculated was 0.56. In question 14, it says the mass m of a metal sphere is given by this expression. So m equals pi times d cubed times rho divided by 6, where rho is the density of the metal and d is the diameter of the sphere. Data for the density and mass are given in this table. So here we are given the density together with its percentage uncertainty, as well as the mass together with its percentage uncertainty. And in 14.1, we have to calculate the diameter d. So we have our equation. In order to find d, we first have to make it the subject of the formula here. So we can start by multiplying through by 6 to get rid of the fraction here. Now we can divide the pi times rho into the 6m. So d cubed will be 6m divided by pi times rho. And then finally, we want to get rid of the cube here on the left-hand side. So we take the cube root on the right-hand side. So now we can find d by substituting in values, the values that we were given. So the mass was 7.5 kilograms. Then divided by pi times rho. And rho was 8,100. Now we can do this on a calculator, and I've worked it out here. We have an answer of 0.1209, etc. Now we're going to write this with two significant figures, so 0.12 meters. And the reason for that is that if we look at the data that we used in our calculation, the density and the mass are both given with two significant figures. And hence our answer for D must be with two significant figures. Then in 14.2, it says, use your answer in 14.1 and the data in the table to determine the value of D with its absolute uncertainty to an appropriate number of significant figures. Now, we are given the percentage uncertainties for rho and m. And if you look at this equation for finding D, we are dividing m by p. The rule says that when we divide quantities, we combine the uncertainties by adding the percentage uncertainties. So before we can find the absolute uncertainty of D, we first have to find the percentage uncertainty. And we said because we're dividing m and p, or m and rho, we add their percentage uncertainties. So it's going to be 5 plus 4%. Now, we are also taking the cube root here. Taking the cube root is the same as raising to the power of 1 over 3, or raising to the power of a third. And the rule says that when we raise to a power, we multiply by the power. So we must multiply this by a third. And of course, this is 3%. Now we can find the absolute uncertainty of D by applying this percentage to the value we got for D. So 3% of 0.12. and we get 0.0036. Now, we're going to write this to or with one significant figure, so 0.004. And the reason for that is we need to write it with one significant figure because the percentage uncertainties here that we used in our calculation are both to or both with one significant figure. So 0.004. We already worked out the diameter here as 0.12. In question 15 it says the time t for a satellite to orbit the Earth is given by this equation. So t equals the square root of kr cubed over m, where r is the distance of the satellite from the center of the Earth, m is the mass of the Earth, and k is a constant. It says in 15.1, determine the SI base units of k. Now, we need to make k the subject in this equation. And we can start by getting rid of the square root and squaring both sides. So we square both sides. The square root falls away. Now we can get rid of the fraction here by multiplying both sides by m. We want the SI base units of k, so we want to isolate k, and we can divide the r cubed into the mt squared. Now we can find the SI base units for k. M is the mass, and that's in kilograms. T is the time, and that's in seconds. R is the radius, which is in meters. But it's radius cubed, so it's meters cubed. We can bring the m cubed to the top. So we get kilograms seconds squared per meter cubed. So these are the SI base units of k. Then in 15.2 it says, data for a specific satellite is given. So we're given values for T, R, and M. These measurements together with their percentage uncertainties. Calculate K and its actual uncertainty in SI units. So we can start by finding K, and remember that we do have a formula where K is a subject. So we merely plug in our values here for T, M, and R. So T, so it's T squared then times M over R cubed. So all over R cubed. Now, we can do this on a calculator, and I've already done so. And this is what we get, 5.917, etc. times 10 to the 11. So 10 to the power of 11. Now, what's important to note, the data that we used in this calculation has a least number of significant figures of 2. So the least number of significant figures in these values will be 2, and hence our answer will also be given with 2 significant figures. So 5.9 times 10 to the power of 11. So that's what we can write in here. We already have times 10 to the 11 here, so we don't have to write it in here. And of course, the question said in SI units, although we haven't found the actual uncertainty yet, and we know that the SI units that we found for K were kgs seconds squared per meters cubed. Now we can proceed and find the actual uncertainty of K. We're given these percentage uncertainties for T, R, and M. So we're first going to find the percentage uncertainty of K. Now, what's important to note here, if we look at this equation, we're multiplying and dividing. And we know that the rule says when we multiply or divide, we add the percentage uncertainties. Then if we raise to a power, like the t squared and the r cubed, we multiply the percentage uncertainty with a power. So we have t squared, and of course, the percentage uncertainty for t is 0.5. Since t is squared, we multiply 0.5 by 2. Then we add. Then we're multiplying by m, so we can add the percentage uncertainty for m, or of m. It's 2. Then we're dividing by r cubed, so we're going to add again, but multiply the percentage uncertainty of r by 3. So it's 3 times 1%. So this is going to be 1 plus 2 is 3, plus 3 is 6. So 6%. We want the actual uncertainty or absolute uncertainty of K. So all we do now is we apply the 6% to the value we got for K. And we get 3.55 times 10 to the 12, or rather 10 to the 10. Now, we need to get it to 10 to the 11, so it's actually 0.355 times 10 to the 11. Now, what's important to note is that these percentage uncertainties all had one significant figure. And that means that we must give our answer here to one significant, or with one significant figure. So this will become 0.4 times 10 to the 11. Then in question 16, we have a smooth pebble made from uniform rock that has the shape of an elongated sphere, as shown here. It says the length of the pebble is L. The cross-section of the pebble in the plane perpendicular to L, so in the vertical plane, is circular. So circular with a maximum radius of R. So the radius varies from place to place, and the maximum radius is R. A student investigating the density of the rock makes measurements to determine the values of L, R, and the mass M of the pebble. And we are given these measurements. So L, the measurement for L here, for R here, for M, together with their absolute uncertainties. In question 16.1, we have to state the name of a measuring instrument suitable for making this measurement of L. So this measurement here. Of course, L has a length or value or measurement of 0.1242 meters. If we multiply this by 100, we get 12.42 centimeters. Now, in order to answer a question like this, you need to be familiar with the information about these three measuring instruments used in a laboratory to measure length width. The first one is the micrometer screw gauge, and we can just call it the micrometer. It can measure a maximum length of 25 millimeters. So you have to memorize this. The precision or resolution of the micrometer is 0.01 millimeter. So you have to memorize these two values, and you can always convert it to centimeters or meters where necessary. Then the second instrument is the vernier calipers. The maximum length that it can measure is 15 centimeters or 0.15 meter. This you also have to memorize. And the precision is 0.1 millimeter. Then we have the meter rule, which can measure a maximum length of 100 centimeters or 1 meter. And it has a precision of 1 millimeter. So this is the smallest division on a meter rule. So the green underlined here, you have to memorize. Now, let's see whether we can eliminate one of these or some of these. If we go back to the length here, the length of this pebble was measured to be 12.42 centimeters. The micrometer can only measure up to 2.5 centimeters, so we can eliminate this option. So it's between the vernier calipers and the meter rule. Because the vernier calipers can measure up to 15 centimeters, and the length here of the pebble is only 12.42 centimeters. So it can be one of these two. But now we consider the precision or resolution. The meter rule has a precision of only 0.001 meter, whereas the vernier calipers has a precision of 0.0001 meter. If we look at the error in this measurement, it's 0.0001 meter. And that corresponds to the resolution of the vernier calipers. So it's going to be this one. So the vernier calipers. Then in 16.2, we have to determine the percentage uncertainty in the measurement of R. So we're going to use this equation. So the percentage uncertainty of R will be the absolute uncertainty of R divided by the measurement or measured value times 100. And we can get those values. The absolute uncertainty for R is 0.0004. And the measured value is 0.0420. So 0.042. And multiplied by 100. So let's calculate that. And we get 0.952. Now, what's important is that The absolute uncertainty of R is given with one significant figure. So we need to give the percentage uncertainty also with one significant figure. So the final answer here will be 0.952 rounded to 1%. So we have one significant figure. Then in question 16.3, it says the density rho of the rock from which the pebble in 16.2 is composed is given by this equation. So the density is mr to the power n over kl, where n is an integer and k is a constant with no units, and k is equal to 2.094. Use SI base units to show that n is equal to -2. So let's do that. We can start with the left-hand side. The density SI units, or the SI units for density, we know that density is mass per unit volume. So we measure mass in kilograms and volume in meters cubed. So kilograms per meter cubed. This will go on the left-hand side. On the right-hand side, we have the mass m, which is in kilograms, the radius r, which is in meters, so meters to the power n, all divided by kl. Now, it says k doesn't have any units, so we can ignore k. L, of course, is the length, and that's in meters. We can simplify the right-hand side here. And remember the exponential rule that says when we divide numbers with the same base, we can subtract the powers. So we can use that rule. So on the right-hand side here, we'll have kilograms, meters, and in n minus 1. So meters to the n minus 1. We can cancel the kilograms on both sides, and we have m to the -3 equals m to the n minus 1. Now we can use another rule of exponents, or law of exponents, which says when we have an equation and the bases are the same, the powers must be equal. So we can see that n minus 1 must equal -3. And solving for n, we'll have -3 plus 1, which is -2. Then in B, we have to calculate the percentage uncertainty in rho. In other words, in the density. And earlier on, we were given this equation for the density. It's equal to mr to the power n over kl. And we calculated the value of n. We saw that it was -2. So we can rewrite this equation as mr to the -2 over kl. Also remember that k is a constant with no units. Now, to get the percentage uncertainty in rho, we're going to do the following. Recall that when we multiply and divide quantities, we combine the uncertainties by adding the percentage uncertainties. So we have to add the percentage uncertainty of m to that of r and then to that of L. So the percentage uncertainty in rho will be the percentage uncertainty in M plus the percentage uncertainty in R plus the percentage uncertainty in L. And we can ignore K because it's a constant. We're also raising r to the power of -2. And the rule says that when we raise to a power, we multiply by the power. So we need to multiply the percentage uncertainty of r by the power. In this case, the power is negative. but we never multiply by a negative power. So we're going to multiply by positive 2. And that is because an uncertainty can never be negative. So when the power is negative, we change it to a positive when we multiply the percentage uncertainty by it. So delta M over M over 1.072. Then delta R over R, so it's 0.0004 divided by 0.0420. And of course multiplied by 2. Then plus delta L over L times 100. This we can do in a calculator, and we get an answer of 2.078. So 2.078. These absolute uncertainties that we used in this calculation are with one significant figure. So our answer then will also be given with one significant figure. So it's going to be 2%. In C, it says determine rho with its absolute uncertainty. Give your values to the appropriate number of significant figures. So we have the equation for rho. It's going to be mr to the n, and we saw that n was -2 over KL. So we can plug in the values. So the mass M times R to the -2, all divided by K, the constant. We were given this value in the question, the value for K, and then times L in the denominator. And this, of course, we can do in a calculator. And we get an answer of 2336.67, and we can round it off to 2337. Now, this, of course, is kgs per meter cubed. We need to write the final answer with the correct number of significant figures. If we look at the number of significant figures for each value in our calculation, we see that we have 4 significant figures here, we have 4 here, 4 here, here we have 3 significant figures. So our answer must be written with the least number of significant figures used in the calculation. So we have to write this answer with 3 significant figures. So 2337 with 3 significant figures will be 2340. We still have to find the absolute uncertainty in the density. Now, recall previously we calculated the percentage uncertainty, and it was 2.078%. Our final answer was written to one significant figure as 2%. So we want to use this percentage uncertainty to get the absolute uncertainty in rho. So then the absolute uncertainty in rho will be the percentage 2.078 divided by 100 multiplied by the value we got for rho. And this we can find on a calculator. and we get 48.56. Now, deciding on the appropriate number of significant figures. The absolute uncertainties here were all given with one significant figure, which means that we must round this so it has one significant figure. This is approximately 49, which is still to two significant figures. So our final answer will be 50. So our answer is with one significant figure then.